Hello everyone. Again let us continue with the analysis of statically indeterminate truss using method of consistent deformation. Now this is the last class of this week. I believe by now you have at least understood the concept and its application to indeterminate trusses. Just to reinforce your concept, reinforce the understanding of the method, let us take the final example of this week. Now, in this example, okay, so this example is this. It is again an indeterminate structure, indeterminate truss. Let us find out what is the static indeterminacy in this case. So, the number of joints we have 1, 2, 3, 4, 5, 6, number of joints j is equal to 6, j is equal to 6. So, number of equations available 2j, which is 12, and then number of reactions, we have 2 reactions here and then another 2 reactions here, total reactions R is equal to 4, and then number of members 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, member is 10. So, number of unknown is m plus r, which is 14, and number of equations available 6 into 2, 2 per joints 12. So, Ns is equal to Ns become 2. Okay. Ns is equal to 2. So, static indeterminacy for this problem is 2. Now, see whether it is external indeterminacy or internal indeterminacy. You see here the number of reactions are 4, but in this truss if we instead of hinge support here, if we provide a roller support at D, then also the structure is stable. So, the additional horizontal constraint at D that makes the structure indeterminate. So, one indeterminacy is due to the additional horizontal constraint at D, and then another indeterminacy. So, this is external indeterminacy. So, the structure has external indeterminacy 1. Similarly, structure has internal indeterminacy 1, because you see whether one of the diagonal members, this member or this member, they are additional. Even if you do not give them one of them, then also the structure is still stable. So, the presence of this diagonal or this one of this member make the structure indeterminate. So, that indeterminacy is internal indeterminacy. The structure has one external indeterminacy and one internal indeterminacy. So, total indeterminacy is 2. So, this is the first step, and the second step is identify the redundant force. So, we need to since indeterminacy is 2, so we need to identify 2 forces. One is associated with the reaction and one is associated with the member force. So, what redundant force we take? We take dx as redundant. So, and then so member BC, say member FC. So, the force in member FC we take as redundant. Okay. So, this is external redundancy, this is the reaction at D, and this is the force in member FC. Okay. Okay. So, let us see this is the example we have. So, just in order to identify the members, let us give some numbers to them. This is 1 and then this is 2, this is 3, then finally this is 4, okay, this is 4, this is 5, this is 6, 7, 8, and then this is 9, and then this is 10. Okay. So, in this case Ns is equal to 2, one is external, one is internal, and then we take our what is this reaction dx, say dx is equal to x1. So, it is the first redundant, and then we take F member force F10 as x2. Okay. So, these are our 2 redundant forces. Okay. Now, so x1 is our first redundant and x2 is our second redundant. Okay. Now, let us find out. We need to decompose, we need to divide the structure into now primary structures. We have three such primary structures, determinate structure. One is we need to remove the redundant. One is the primary structure subjected to the external load, and then primary structure subjected to redundant force. Since we have two redundant forces, so there will be two primary structures subjected to, in two cases we have, like the previous example. So, the structures will be, the first will be this, and then it is roller support, hinge support here, roller support here. So, this becomes A, B, C, D, E and F. It is subjected to horizontal, this is the external load, which is 2p, and then p, and then p here, and so this is first primary structure, and then the second is the same structure, then this is A, B, C, D, E, F, and then this is, so member 10 is removed here and the horizontal constraint at D is removed here. Okay. And this is subjected to, first is this unit load, which is x1 is equal to 1. Okay. So, this is first, and the second will be roller support A, B, C, D, E, F, and then this is the member, and second primary, second redundant force is this is, and this is 1. Okay. So, in this case x 2 is equal to 1. So, this is x 1 and this is x 2 here. So, this will be this will be this plus this plus this. Okay. So, next step is we need to, we have already the first step and second step the both first two steps are done. Then the third step is to solve it, find out the forces, member forces here, and then the fourth step is find out the member forces in this and in this. So, again these are all, these structures are statically determinate structure. So, we can find out the member forces. So, I have the member forces with me. What I will do is I will just give you the what are the forces. Okay. Now, we have 10 members here. Again, you can, it is very convenient to write this in a tabular form, but because of this space I could only do up to this part, but you can have some more columns here where you can actually determine those displacement and flexibility coefficient in the table itself. Okay. So, that will be convenient. So, we have total 10 members. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the lengths are these are all 45 degree. Intentionally I took 45 degree because then the computation is slightly easier. Okay, calculation becomes slightly easier. Now, all these vertical and horizontal rail length or diagonals are root 2L. So, these become L, member 3L, then member 4 is diagonal. So, this becomes root 2L, L, member 7 is again, member 7 is diagonal, root 2L, then L, member 9, and for all it is AI. So, AE. So, they are same, but again you can have different values of AE for different members. So, we can compute the flexibility for each member separately in this column. Okay. Now, you can see there are 3 columns here. First is external load, the forces due to external load, forces due to the first redundant, and forces due to the second redundant, and these values are this is 7 by 3 p, this is again 7 by 3 p, this is 5 by 3 p, this is minus root 2 by 3 p. Please you do not take these values, please compute these values and proceed and then proceed with the calculation. Okay. Here the idea is to demonstrate the concept. There is okay, let me see, member 5, member 6 is 5 by 3 p, member 7, and then member 8 is p by 3, member 9 is minus 2 root 2 by 3 p. I do not know whether it is properly visible or not, but that is not important. What is important is to get the to understand the concept. So, these are the external load for this case. So, this is our step 3. Step 3. Okay. Now, step 4 is find out the forces in this structure and this structure. You can again do that, but again let us see whether we can slightly reduce the problem by identifying the member force, identify the zero force members or not. Now, you see this is look at this joint, this is a zero force member, okay, and then if this is a zero force member, then also you see since this force is being applied here, your reactions are, if you take moment about A, this will not contribute to this moment. So, reaction at point D, dy will be 0. So, for this case dy will be 0. Since dy is equal to 0, ay will also be 0 and ax will be 1. So, since dy is equal to 0, then this is also a zero force member, because that this its vertical component, there is no force to balance the vertical component here. Now, if this is equal to 0, then what happens if you take joint C here, it has horizontal force, vertical force, in horizontal and vertical force there is no other forces to balance them. So, these two forces will again be 0. Now, again if you take point joint E here, this force, this member will have a vertical component, but there is no other vertical force to balance them. So, this will also be 0. Now, remember the force, the Ay, we have just obtained that Ay is equal to 0. Now, if Ay is equal to 0, then this member has vertical component which won't be balanced by anyone. So, this will be 0. So, you can see that all the member forces are 0 here except in the horizontal member. By intuition we can say that, because you are applying the force along this line. So, all these forces you get, all these forces you will get 1. These values are, all these values are 1, all these values are 1. Okay. So, then in 1 you will get the first, second and third members, you have the forces which is non-zero and the values are 1, and all other members the forces are 0. So, write down these values are 1, first member, second member, third member, and all other members these values are 0. Okay. Now, similarly, let us do it for this structure. Now, again like previous one, if you take these two forces are collinear, they whatever components you take, whatever point about which you take the moment, these two forces will cancel each other, balance each other. So, what you get is all these reactions at D and reaction at A, all these reactions will get 0. So, in this case you get dy is equal to 0, in this case we will get Ax is equal to 0 and then Ay is equal to 0, Ay y is equal to 0, all the reaction forces are 0. And if you now if you apply the similar logic, then what we get is we get these forces, these members are 0 force member. Okay. See, it is very important step to identify a 0 force member, because once you identify them, your computation become very easier or reduced rather. Now, so then rest we need to find out the forces in these 5 members, and these forces will be, let us write the forces, and these values will be, okay, the first member it is 0, and then it is minus 1 by root 2, and then 0, 0, 0, then minus 1 by root 2 again, minus 1 by root 2 again, 0, minus 1 by root 2, and then 1 and 1. So, this is n capital N I, and this is small n I 1, and this is small n I 2. This is associated with the first redundant, and this is associated with the second redundant, and it is due to the externally applied load. Okay. Now, again we can write the flexibility format like this, d1L d2L plus, this is the compatibility condition, F11, F12, F21, F22, x1, x2, that is equal to 0. That is the compatibility condition. And what is d1, d1L and d2L? d1L is equal to, d1L is this is our first redundant. This is our first redundant is horizontal force reaction at D. So, d1L will be the horizontal reaction at D due to externally applied load, and d2 will be horizontal deformation in member FC due to the externally applied load. Okay. So, this is the deformation due to externally applied load. Now, F11 is the flexibility associated with x1, or the force applied in x1, and displacement is measured along x1, and F12 is equal to force applied in direction of x2, but displacement is measured in the direction of x1, and similarly F21 is equal to force measured in the direction of x2, but the force is applied in the direction of x1, and F22 is for displacement measured in the direction of x2, force is also applied in the direction of x2, like previous example. And then we can write that d1L is equal to summation of I, in this case I is equal to 1 to 10, then Li by AIEI, and this is Ni in small n I 1. Okay. And please, this is very important, and this is d2L is equal to summation of I is equal to 1 to 10, and then Li AIEI, and then capital Ni small ni 2. Okay. So, this is due to the this is in the direction of second redundant, it is in the direction of first redundant. Similarly, F11 will be I is equal to 1 to 10, same Li by AIEI, and then Ni1 square, and F22 is I is equal to 1 to 10 Li AIEI, and then Ni2 square, and finally F12 is equal to F21, you can write I is equal to 1 to 10 Li by AIEI, and then Ni1 Ni2, or Ni1 Ni2. Okay. Now, so this is the flexibility coefficients. Now, we can calculate these flexibility coefficients and write here, and then final expression what we get is like this. I will give you the final expression for this, and the final expression becomes d1L is 6.33, and d2L is minus 5.105 P plus F11 you get 3 and F12 is minus 0.707, it is symmetric 707, and F22 becomes 4.828, that is then x1 x2 is equal to 0, and finally you get x1 is equal to, if you solve them, minus 1.93 p, and x2 is equal to 0.775 p. Okay. So, once we know x1 and x2 are essentially now that was the redundant forces. Once we know the redundant forces, rest of the thing is then with the knowledge of these redundant forces, value of the redundant forces, the structure become statically determinate. Now, we can find out the support reactions on forces in other members. Okay. So, this is how we can apply a method of consistent deformation for trusses. Now, for demonstration purpose, we chose some example which has 1 or 2 redundant forces, but in actual structure you can have many redundant forces. But if you have that, then your equation becomes something like this. If you have say 4 redundant forces, then it becomes D1L, D2L, D3L, D4L, and then plus this is F11, 12, 13, 14, 21, 22, 23, 24, and then F31, 32, 33, 34, and finally F41, F42, F43, F44. That into x1, x2, x3, x4, that is equal to 0. That your compatibility equation. You have, if you have n number of unknown, then this flexibility matrix becomes n by n, but these remain always symmetric. So, these always symmetric. Okay. These always symmetric. This is a symmetric matrix. Okay. So, the concept is again same, only thing is you need to your computation is the calculation is required calculation is more when you have problem, you have more number of redundant forces. As I said earlier that if you look at all these steps, the first step is very straightforward. Then step number 3 to step number 6 is also very straightforward. It is once you know the procedure, you can apply that procedure to any problem. Step 2 is very important, where you need to identify the redundant forces. Okay, you need to identify the redundant forces in such a way that primary structures are determinate structure, but you cannot afford to have an unstable primary structure. Okay. So, at step 2 you need to apply your whatever structural engineering sense you have is developed so far, that you need to apply. You need to understand how the behavior of the structure. I have already told you in the first class, but I am repeating it, and probably I will be repeating many more times, that calculation is fine, but before actually you do the calculation, you need to understand the problem. You need to try to analyze the problem in your mind, and you need to solve the problem in your mind, and the calculation is required finally to get the numerical values. Okay. With this I will stop here today. So, what we have done, we have seen the demonstration of method of consistent deformation for trusses. Next week, we will see how the method of consistent deformation can be used to analyze statically indeterminate beams and frames. Okay. With this, thank you very much. See you in the next week.